Can you get 3? 1, 2, 3. Oh, 2.5. Oh, that was close enough. Close enough. Within epsilon net, anyways. Ah, 3. Third term's a charm. This is the Tutor Wizard. What we're doing again is this is going to be another video on the Math 120 coronavirus outbreak self-isolation scenario. So here we go. Last time what we were doing was we were looking at invertible matrices. I did a 3x3 matrix and I did it the two ways. You can write down block A, block I3 is what I did, and then you can row reduce it and either show it exists or get a row of zeros. We're going to do that again today, don't worry. And then the other way that we do that is we used a bunch of cofactors. So let's rewind a little bit and recap, and then we'll move forward from there. What we've got here is the definition of an inverse again quickly. We call a matrix, which is n by n, the inverse of an n by n matrix if when you multiply them together in either direction, you get the identity matrix. That's our definition, and that's actually an extremely useful thing that we're going to use in our algebra also when we try to solve equations algebraically for a matrix X or something like this. I'll also show you an example of that, what I'm talking about. But when we want to manipulate or solve a matrix equation now for X or something like that, you have to use the matrix multiplication and the rules that go along with that. You can't just flip them all the time. A times B doesn't equal B times A and all of these types of things. We're going to list out a bunch of the properties of what inverses are. We call B the inverse of A if we have this. The other thing I want is if it is invertible, we actually classically call B A inverse. So the property that we actually have, the first thing you want to keep track of is if A is invertible, this says that A times A inverse is equal to the identity matrix, and A inverse times A equals the identity matrix. What that's really telling us is if you have A or its inverse in an equation, you want to get rid of it, you multiply by the other one on both sides so that you can create identity matrix. The other thing we know is, which will become extremely useful before we go forward, is IN times A is A for every matrix, and A times IN is also A for all of these square matrices. These are the first rules that you're allowed to do to manipulate equations. Let's look at the properties of inverse before we compute again a couple more inverses, but I forgot to squeeze these in last time. The theorem is going to say let A and B be invertible. Then what we get is A invertible implies A inverse is unique. You can't have two different inverses for a matrix. 2. If you have, I like this one a lot because if you have 2, the number, what's the inverse of 2? Usually you don't write it like that. You write it like 2 is 1/2. And then what's 1 over 2? 2. What that says is the inverse of the inverse is the number again in number land. It's the same thing is true for matrices. A inverse is the matrix again. 3, I have to sneak in a definition. Definition. A to the 0 is the identity matrix, and A to the n is equal to A times A n times, just like for numbers, if n is a positive integer. Why do I want that? Because we forgot to give this definition probably 2 somewhere along the line, and I want to say property 3 is A to the n's inverse is the inverse of A to the power n. If you're seeing that for the first time, basically it says you can switch the exponent and the inverse. Again, this is not exponent laws per se. This is the multiplicative inverse of the A multiplied by itself n times, and that's equal to the inverse of A multiplied by itself n times. That's what it's technically saying. And then 4. The other one you need to, this is the most important one when you're going to use it. This is extremely useful when you do inverse of inverses A. This is useful in arguments. If the inverse is unique, this helps us in a lot of other proofs of stuff. And it will in particular help us with this one, because what it says is, notice, if you have A times B matrix multiplied and then you take the inverse of that matrix is invertible, but its inverse is B inverse A inverse. Long story short, if you try to distribute that in, you can't just distribute that in. It's not a regular exponent. It reverses them. And remember, matrix multiplication is non-commutative, so in general that does not equal A inverse B inverse. This is the most important one. And then this one. Now let's do a practice one more time. Some 3x3 matrices and finding their inverses both ways. What we're going to do is we're going to find the inverse of two matrices or show that it doesn't exist. What I'll do is I'll do this matrix first. I'll do both methods to show that it does the same thing, and then I'll do both methods for this. Since we're recording it, we might as well do the gritty details. Usually when you're in a lecture, they're going to, what the scenario of what's happening is, I need to show you how to do the two methods on 3x3 or larger in matrices. This takes a long time, and then I have two methods, but usually they'll show you one method with one or one method with the other, and maybe it exists or it doesn't exist. What I'm about to do is 4 different techniques. I'm going to use this matrix, and then I'm going to use row reduction method to show the inverse exists. Then I'm going to use the other method, the formula, the cofactor, and the adjoint method to find the inverse of this matrix. Turns out this matrix has an inverse. This one doesn't. So then I'm going to use the row reduction method to show it doesn't have an inverse, and then I will compute the determinant or use the cofactor method to argue why it doesn't exist. We have 2 methods of finding inverses. At first you might want to just pick one of those methods that you like and stick to it, even though it's complicated. Again, what are the benefits? The pros of the elementary matrix or the row reduction method is that you don't need any new machinery. You learned row reduction to do for a bunch of different problems. You're probably, hopefully, fairly good at row reduction by now, and it gets you the inverse of any size matrix. Good. The con is fractions abound. When you have horrible numbers, or remember I have to put the block identity matrix behind this, which is what we're going to do, and I have to row reduce all the way to reduced row echelon form. For a 5x5 matrix or something like that, that might be all fractions, and there's so many steps, and you may not like doing that. That's the default of this method. The con of, let's do it in reverse now for the other method. The con of what you argue, what you don't like about the 1 over determinant adjoint method is all of a sudden there's these fancy words and a bunch of machinery, and then adjoint is cofactor transpose, and you're like, what is transpose? And then you've got cofactors and you're like, I don't want to do this anymore. So you're like, and you told me that there was this Gaussian Jordan elimination method I have, so I already know how to do that, so I'm going to stick to that. That's the con. There's so much more machinery and things, sophisticated terminology and machinery we have to learn how to use this formula. But this is the inverse. Why is this beneficial? You'll see again, and I'll remind you when we do this, if the matrix A has no fractions, then when I compute this adjoint, which is just cofactors, there will be no fractions because I'm just multiplying and adding and subtracting these numbers, so you'll never get fractions. Closure of scalar multiplication and addition for integers. And then all the fractions come when I multiply the determinant at the end. Those are the pros and cons, the one pro and the one con of both of those methods. I prefer this one much more than the Gaussian elimination. The fact that the fractions come at the end far outweighs the fact that I have to learn how to do a bunch of cofactor computation. That will get easy eventually in the month you have left to do this stuff. It'll become really easy when you do it 1,000 times, and then we're off to the races, and this is much faster and much more enjoyable. Let's do it. I'm gonna guess as a check theorem, A minus 1 exists. I'll be lazy. Let A be an n by n matrix. This exists if and only if the determinant of A is not 0. I don't know if I said it last time, but I'm saying it now. This is probably one of the only things I hope that you learn out of matrix theory, and especially this video or the last few. Inverses exist. The multiplicative inverse of a matrix exists if and only if this determinant is not 0. It's almost as if the determinant determines this. I'm going to make up the fact that that's the genesis. I don't know if that's why they call it determinant. No, it's probably not. It determines stuff for us. It determines areas. It determines volumes. It determines whether you're invertible. Determinant. In either method you use, this may be a useful thing to check before you compute all those horrible cofactors or those businesses. Compute the determinant quickly. Can we do it in our head? The determinant is going to be 1 times, no we can't, 1 times 40. This says the determinant of A, in this case I'm going to compute is, I'm going to do cofactor expansion along the top row and just be lazy. It's 1 times this subdeterminant, which is 1 times 40, minus 2 times, now we're going to block off this and this, so we're going to get 16 minus 3 is 13. So we're going to get 26, and then plus 3 times 0, negative 5. So we're going to get 40 minus 26 minus 15, which is 40 minus 41, which is negative 1. What does that tell me also? The inverse has no fractions because they're all going to be 1 over minus 1 when we introduce fractions even. This is not 0. The inverse exists. The determinant of this matrix is non-zero, so the inverse exists. Now I know I'm not wasting my time looking for it. Coincidentally, I computed several of the cofactors. We'll do it again because nobody likes watching me do that. Cameraman says, stop talking while you're erasing. I'll do what I want. I know the inverse exists. I just computed the determinant's negative 1, and the inverse won't have any fractions. Let's do what I consider the horrible version of row reduction and Gaussian elimination. What I'm going to do is write it as A block identity. Now I have to turn this into the identity matrix or show it has a row of zeros, but we know it's going to turn into the identity matrix. We know it's going to happen because I already computed the determinant. I know the inverse exists. This is the peace of mind of why I've done it. You should know by now, get a leading 1, which I have, and eliminate these two. So 1, 2, 3, 1, 0, 0. First I'm multiplying by negative 2. 2 minus 2 is 0. 5 minus 4 is 1. 3 minus 6 is negative 3. 0 minus 2 is negative 2. 1 minus 0 is 1. 0 minus 0 is 0. Now I'm multiplying by negative 1. 1 minus 1 is 0. 0 minus 2 is negative 2. 8 minus 3 is 5. 0 minus 1 is minus 1. 0 minus 0 is 0. 1 minus 0 is 1. I've been doing this a lot of years, and I'm still going to use my fingers, and people try to get around it, but I'm not going to make mistakes that way. I will make mistakes that way, but I'll minimize them. Just a human. Now what? I've got a leading 1, eliminate below. The symbolization just reversed itself. Squares and circles, circles and squares. Get rid of the 2. I'm going to multiply this row by positive 2 this time. 1, 2, 3, 1, 0, 0, 0, 1, negative 3, negative 2, 1, 0. Those rows I'm not changing, so I quickly copy them down. This is how you do this fast on an exam. Now I turn Thinky Brain on. 2, negative 2 plus 2 is 0. 5 plus negative 6 is negative 1. Negative 1 plus negative 4 is negative 5. 0 plus 2 is 2, and 1 plus 0 is 1. Now I want them to be lazy and multiply this row by negative 1. There, I just did. Are we done though? This row is, because this row is the identity matrix. This is the last row of the inverse. So this row is done. These aren't. Why? Because these have to go. And first what I'm going to do is the circle one first. Now in reverse, we've just made it upper triangular. All the information's in the upper triangular and there's zeros below. Now we have to make it lower triangular as well to get zeros in the above. To do that, now what we're going to do is row 3 and row 2 are going to manipulate. First I'm going to kill these ones by using row 3, then I'll get rid of this one using row 2. So these ones go. So what does that give me? 0, 0, 1, 5, negative 2, negative 1. Now that row is not going to change. I'm going to manipulate this 0, 1, and then what are we doing? We're multiplying by positive 3 the first time. So now what I'm doing is 1 minus 1, 0 is 1. Negative 3 plus 3 is 0. Negative 2, really? Plus 15 is 13. 1. The numbers are getting big. Am I doing it right? Stick to your guns. 1 minus 6 is minus 5. 0 minus 3 is negative 3. Now I'm going to multiply by negative 3 to get rid of this one. So I'm going to get 1, 2, 3 minus 3 is 0. 1, even worse. No. Minus 15 plus 1 is negative 14. 0 plus 6 is 6. 0 plus 3 is 3. And I want to get rid of this guy, and then we're done. That will give me 0, 1, 0. Also notice that this is now the second row of the identity matrix, so now this row is done. If we did it with no mistakes. Again, there could be mistakes, I don't know. 0, 0, 1. And then I'm doing 5, negative 2, negative 1, 13, negative 5, negative 3. And what are we doing? Now I'm multiplying by negative 2 and adding it to this. So what am I going to get? We get 1, 0, 0, 14, negative 14, minus 26, negative 40. Those numbers are so big, it's got to be wrong. No, I'm pretty sure that's right. 40. Now I'm going to get 6 plus 10 is 16. And then 3 plus 6 is 9. I'm so not confident about my numbers. How could I ever check? Multiply this by this, and I get this if it worked. Let's try that out. What that says is this is the inverse matrix of A. If I'm worried about it, and again, they train you in high school or K to 12 to be like, oh, the numbers should be nice and small and they should never be fractions, otherwise you did something wrong. And they're like, oh, my numbers were bigger than fractions. No, the universe doesn't care whether the numbers were horrible. When you do real science, it's going to be a nasty numbers, and there's always going to be fractions. That's secret. There's always going to be fractions. If I assume, or if I'm worried about this being the wrong calculation, this problem specifically has a way out always. What is that? Multiply. Again, we'll check. This is 3 by 3, and this is 3 by 3, so the inside indices match, so it's well posed, and the outside is 3 by 3. And what am I going to get? Let's check. Negative 40 plus 26 plus 15 is 41 minus 40, which is 1. Huh. And then I get 16 plus negative 10 plus negative 6 is 16 minus 16, which is 0. Then I get 9 minus 6 minus 3 is 9 minus 9, which is 0. 0, 1, 0, 0, 0, 1. Yeah, it worked. You have a check on the exam. This is the inverse. Now let's see if we can get it the other way, the much faster way. Let's leave them both up there and see what we get. To do it the other way, what I first need is I'm going to need the cofactor matrix transposed, and I need the determinant of A. 1 over the determinant times this is what I need. Those are the two things I need. And noodles. We need some noodles. This is Noodles. He's going to do some cofactors with us. See how far we go, right? You like cofactors? That's a good boy. So what I'm going to do is we're going to look at the first 3 cofactors like I did at the beginning. And I don't even want to see the cofactors. There they are. That's the little matrices, the original ones. Then we'll do it. All right. You just want to climb on everything. What was I doing? Cat time. Now he's harassing the cameraman. I'm going to cofactor or expand along the top row. What do I need for that? Cauchy says the determinant of A is A11 C11 plus A12 C12 plus A13 C13. So what I need is, I need C11 is negative 1 to the 1 plus 1 M11, which is M11, which is equal to 5308, which is 40. C12 is negative 1 to the 1 plus 2 M12, which is negative M12, which is 2138, which is equal to 16 minus 3, which is negative 13. And C13 is equal to negative 1 to the 1 plus 3 M13, which is M13, which is equal to 2150, which is negative 5. That says now I've computed the cofactors I need. That's this guy, and this guy. These guys come from the matrix A11, A12, A13. So this is equal to 1 times 40 plus 2 times negative 13 plus 3 times negative 5, which is negative 1. That tells me that the inverse exists, and now we have to compute all the cofactors. So I'm going to keep that. The determinant of A was negative 1. Now I'm going to push these cofactors back, 40, negative 13, negative 5. Now that we've computed that and I have the determinant, I need to compute the other cofactors. C21 is negative 1 to the 2 plus 1, M21, which is negative M21, which is negative times 2, 1, 2, 1, 2, 3, 0, 8, which is negative 16. C22 is negative 1 to the 2 plus 2, M22, which is equal to M22, which is equal to the Greek cross blocked off 1, 3, 1, 8, which is 8 minus 3, which is 5. Beep, beep. Turn your cell phones off. C23 is equal to negative 1 to the 2 plus 3. You're never going to stop the train. 2, 3, which is negative M23, which is negative 2 and 3, which is 1, 2, 1, 0. Which is 0 minus 2 minus gives me 2. C31 is equal to negative 1 to the 3 plus 1, M31, which is M31, which is equal to what? I don't know. We're going to block off 3 now. 3, 1 is going to be this guy. 2, 3, 5, 3, which is 6, minus 15, which is negative 9. C3, 2 is negative 1 to the 3 plus 2, M3, 2, which is negative M3, 2, which is equal to 1, 3, 2, 3, which is 3 minus 6, which is negative 3. 3 gives me a 3, and then I get C3, 3 is negative 1 to the 3 plus 3, M3, 3, which is equal to M3, 3, which is equal to 1, 2, 2, 5, which is 5 minus 4, which is 1. What does that give me? An aneurysm, because I'm going to pass out from not breathing. That gives me the cofactor matrix. This tells me how am I going to write that in there. The cofactor matrix now is equal to 40, negative 13, negative 5, negative 16, 5, 2, and negative 9, 3, 1. This means that A inverse is 1 over the determinant of A times the cofactor matrix transposed, which is 1 over negative 1 times 40, negative 16, negative 9, negative 13, 5, 3, negative 5, 2, 1, which is, if I put the negative in there, is negative 40, 16, 9, 13, negative 5, negative 3, 5, negative 2, negative 1. The same matrix. We have two methods of computing the same thing. That was when it works out and the inverse exists. The other method, we're going to do it again. You're like, no, I don't want to see it again. I don't really want to do it again either. But this time I picked one. That's why I did this one first. The other one doesn't exist. It won't take us as long. You're praying for it doesn't exist. It exists on your exam. I guarantee it. It exists. For the next one, we'll do the row reduction business first, and then we'll actually see that we could compute the determinant and seeing that it didn't exist that way. Again, I have a leading 1, so I have to get rid of the 2 and the negative 1. So let's do that. 1, 6, 4, 1, 0, 0. And then I'm going to multiply by negative 2 the first time. 2 minus 2 is 0. 4 minus 12 is negative 8. 1 minus 8 is negative 9. 0 minus 2 is minus 2. 1 minus 0 is 1. 0 minus 0 is 0. Then we're going to just add them this time because I have negative 1. So negative 1 plus 1 is 0. Don't use that finger. You can use a different finger. I'm using that one to point now. 2 plus is 8. 5 plus 4 is 9. 0 plus 1 is 1. 0 plus 0 is 0. Okay, you didn't have to do that the whole time. I did. Luckily, goose eggs were done. You can see it now. Let's manipulate. Let's add those rows together. 1, 6, 4, 1, 0, 0, 0, negative 8, negative 9, negative 2, 1, 0, 0, 0, 0. So I'm just adding, and then I'm going to technically get negative 1, 1, 1. This row of 0 says you can say a minus 1 does not exist. That's what they're telling you, and that's why we had to show you at least once. It doesn't take that long to get there usually, but as soon as you get a row of zeros when you're doing that, that says I can never make the identity matrix, so how could I ever have the inverse magically appear in the back? It won't, magic or otherwise. It doesn't exist. How could we have done that the second way before Noodles continues to harass everyone? The second way is what we can do is just compute the determinant of this original matrix. Doing that, the determinant of A is 1 times C11, which is blocking off row 1 and column 1. So 4, negative 1, 2, 5, minus 6 times, using cofactor expansion, 6 times 2, negative 1, negative 1, 5, plus 4 times the cofactor, this one, 2, 4, negative 1, 2. That is now equal to 1 times 20 plus 2 is 22, minus 6 times 10 minus 1 is 9, and then plus 4 times 8. Is that right? And then what do we get? 22 minus 54 plus 32, 0. So the determinant of 0 says a minus 1 does not exist. That was my not thinky brain, I think. I don't know what was happening there, but that was not thinky brain. More. Now what we're going to do is, now that we have inverses, we are going to discuss in the next section in the chapter usually is how to compute the determinant and do the properties of determinants using n for n by n matrices. Now that you see that we have a method that involves both computing the determinant, both determines whether an n by n matrix, regardless of the size, whether it exists or not, and to actually compute in the formula, we have to compute determinants. We really want to be good at computing determinants of large matrices. It turns out to compute a 10 by 10 determinant, by the definition, we would have to do over 10 million multiplications and subtractions and addition type formulas or computations. And I don't want to do that. You don't even want to see the horrible definition of what the actual definition of determinant is for large of them. What we're going to do is create properties. We have 3 properties that look like row operations, but they're not. Now they're determinant operations, which compute a determinant. And then we're going to use them to efficiently compute determinants. What I'll do is run them on these types of matrices to show you that I can compute the determinant even faster than using cofactor expansion along the top row. And that will be the idea. It's going to be Matryoshka dolls of one determinant all the way down. The way Dr. Solomonovich does this in the book is he defines 1 by 1, 2 by 2, and 3 by 3 determinants first so that he can use them for cross product and areas and volumes using vectors. But now what we want is to efficiently compute n by n determinants. And therefore I'm going to restate the small ones that we've already seen and then give you the general. I'll scare you with the horrible definition of what it actually is, and you should never want to use that or try to. It would take several courses to explain the moving parts. I'll do it to scare you, but I'm not going to expect that you know how to use it or see it. For 1, when n equals 1, the determinant of a number is the number itself. And coincidentally, we have a condition. As long as the determinant of a, which is itself, is not 0, a minus 1, which is 1 over a, exists. So the determinant condition already works. If you're non-zero, your inverse exists. If your determinant is non-zero. 2, when n equals 2, the determinant of a11, a12, a21, a22 is now equal to a11, a22 minus a12, a21. And notice that there's 2 permutations of 2 things. 1 can go to 1 and 2 can go to 2, or 1 could go to 2 and 2 could go to 1. 1 could go to 1 and 2 could go to 2. 1 could go to 2 and 2 could go to 1. 3, when n equals 3, oh, here we go. The determinant of A11, A12, A13, A21, A22, A23, A31, A32, A33 is equal to what? Oh, I can't do it without the trick. So in the 9 chapters of mathematical art, what they're doing is they're writing this down, the second 2 columns, A11, A21, A31, A12, A22, A32. In this one, we did this, and then we did minus this one. Here now what we're going to do is plus, 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 and then minus, minus, minus. By definition, the determinant of a 3 by 3 determinant is equal to A11, A22, A33 plus A12, A23, A31 plus A13, A32, A21. I put them so their indices link actually cleverly. And then those are the plus ones. And then minus these ones. And notice one of them stays fixed. There's always a fixed point in one of these ones. I don't want to get into it. Why did I mention it then? A31, A22, A13. So 3 goes to 1 and 1 goes to 3, but 2 is fixed. Minus, he's an odd permutation, thus the negative. Minus A32, A23, A11 stays fixed, and then minus A33 stays fixed, and A2 goes to 1 and A1 goes to 2. Now 3 factorial is 6. Here 2 factorial is 2, so there was 2 terms. Each term had 2 things in it. Here 3 factorial is 6, so there's 6 terms. Each term has the product of 3 things in it. This is the definition of determinant. Now let's give it for the n by n cases to scare you and generalize this notion. And there's a few things I won't really talk about. This is not how we're going to compute. We give you these things and then we're going to give you properties and cofactor expansion, and the combination of those 2 things will make computing this much more efficient. You can already see how many things would I have to compute this by definition for 3 by 3. There's multiply, multiply, there's 2 multiplications, 2 multiplications, 2 multiplications, 2 multiplications, 2 multiplications, 2 multiplications. And that's, I don't know how big the numbers are. They could be as big a digit numbers as you want. We can make them small at first, but they could be large numbers. And then I have to add them all together. I don't want to do that. For the n by n case, again, this is to scare you. My master's supervisor was Polish from the era of solidarity in the 80s. And he says to me, as I'm his student, there's only 2 ways fundamentally of motivating people. Fear and reward. And there will be no rewards in this class. So fear. I'm going to put fear. You're never going to use this definition. I don't want you to use this definition. I don't even possibly at first, don't try to understand what the definition is per se. I'm going to do it to scare you. There's a bunch of moving parts here. The determinant of A, n by n, first shown by Cauchy, extending this 9 chapters of mathematical art, is equal to the sum over all permutations in the permutation group Sn, which has n factorial permutations, of the sine, not sine trigonometry, another one, plus or minus 1, sine of the permutation, whether he has a number of odd transpositions or even transpositions. If it's odd transpositions, you get a negative. That's where the negatives comes from. If you're an even transposition, you get a plus, times the product of the permutation of all of the indices, 1 sigma of 1, A2 sigma of 2, dot, 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 A-n sigma of n. This is the definition of determinant. To compute a 10 by 10, you would have to, every term is going to have 10 multiplications, and then there's 10 factorial terms in there. I don't want to do that. The internet has to use 5 billion by 5 billion matrices. I don't even want to know what those numbers are. They're huge. How are we going to compute determinants? Not with this hot mess, with something called determinant properties and cofactor expansion along rows or columns. Let's do the cofactors stuff along the rows and columns first, and then I'll show you the 3 properties, and then I want to use the 3 properties in unison with cofactor expansion to create a fast method of computing determinants. I'm pretty sure it's due to Cauchy. Somebody Google it and write, no, it wasn't. Actually, it was this person first. I don't care. Cauchy. What does he say? This is beautiful. What he says is cofactor expansion can be done not along the first row, but any row or any column. What that tells you is for a 3 by 3, I can find the determinant along row 1 cofactor expansion, or another second way of computing it, or a third way of computing it, or a fourth way, or a fifth way, or a sixth way, or the definition 7, or I'm going to get properties which will speed this up. There's going to be many, many ways of computing the determinant. They all have to be the number which is the unique determinant value. So it gives you many ways. If you compute the determinant along cofactor expansion along row 1 and you think, I think I might have done it wrong, well, use a different column or row to do it, and you better get the same number. Otherwise, one or both of those computations is wrong. It gives you a way of checking. At least one of them is wrong. Could be both. I'm not going to make any assumptions. The sheep is half white. That's a joke. I won't do that one later. There's a mathematician and a physicist and an engineer on a train in Scotland. And the engineer says, he sees a black sheep and he says, oh, the sheep in Scotland are black. And the physicist says, no, no, no. All we can say is that in Scotland there is a sheep, at least one sheep, which is black. And the mathematician says, no, 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 this is also incorrect. He says, in Scotland there exists at least one sheep, half of which is black. He makes no assumptions about the other side of the sheep. He can't see it, so how does he know? Gosh, I did it. What does he say? Let a n by n be square, then 1, or let's use I and j cleverly. What's j? I don't know. Number 2 in this case. I can cofactor expand along any row I. The determinant of A is equal to AI1 CI1 plus AI2 CI2 plus dot 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 plus CIN. How did he get first? Because they're commutative, they're all numbers. AIN CIN. That's row I cofactor expansion. Now that says you can use any row I. Notice that the I didn't change. I isn't changing at all. You can write that as a sum. The sum from I equals 1 to n of AI 1 j. I won't do that to you. J. You can cofactor expand along any column j. What does that look like? The determinant of A will equal now A1j C1j plus A1 2j C2j plus dot 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 plus A n j C n j. Now the first index is changing because the rows are changing, but we're in a column now. That is column j. And notice that's saying equal, so all of these things are equal to each other because they're all equal to the determinant. That gives you 2n ways of computing the determinant every time. You can use every single row and you can use every single column to cofactor expand along. So you have 2n ways of computing the determinant, 2n plus 1, because you can use the definition. I dare you. Let's try this out. The idea now is going to be, it says you can use any row or any column to cofactor expand. Use the ones that have zeros. If they don't, use the properties to make zeros, and then use that column. That's going to be my strategy. Let's compute just using this expansion once, and then we'll do the properties, and then we'll combine them together. Matrices bells. Now you can just make it up because I don't really care. I'm just going to cofactor expand. But I have zeros. It would be nice to have. I also put it in row 1 because you know how to cofactor expand along row 1 and it'll save me. But anytime I have zeros, you'll see in my mind you can compute the cofactor if you really want, but I don't need to because it's going to be multiplied by 0. Let's cofactor expand along row 1 and column 1 maybe, and then column 2, and then you'll see that all of them give me the same value, but these ones I'm going to have to compute 3 positive values, and then also you should remember as we go plus minus plus minus plus minus plus minus plus. That's the checkerboard for the cofactors. Here we go. The determinant of A along row 1 is A11 C11 plus A12 C12 plus A13 C13, which is equal to A11 is 1 times C11 is obtained by blocking off row 1 and column 1, 3, 5, 2, negative 1. I know exactly. Now I get a negative from the checkerboard, negative this guy 2. Now I have the minor. The minor is blocking off row 1 and column 2, so I get 1, 5, 0, negative 1, and then plus this times 0, I don't care, I'm not computing it. Gone. That's the whole point of why you want rows or columns that have zeros. Use those ones to cofactor expand along. At first you're like, I just want to use row 1 because it's safe. I know, but you have to expand, otherwise it's going to take you millions of computations to do it and it's not going to be fun. I quit. Equals 1 times negative 3. 3 times negative 1 is what I'm doing, minus 2 times 5. Minus 2 times 1 times negative 1 plus 0 times 5, which is equal to 1 times negative 3 minus 10 is negative 13. And then I get minus 2 times negative 1, which is plus 2, which is negative 11. I don't know, I made it up, but let's see, this is the whole point. You can check, and we'll do it along a different row or a different column and see what we get. This way, if I didn't make a mistake, somebody find it if we did. I got a negative 11 the first time. Let's see if I get the same number or a different one. And that's why I'm saying they're either both wrong or we'll have to check. Cofactor expanding along column 1 now. Again, I have plus, minus, plus is what I need for the checkerboard, this column. Cofactor expansion along column 1 is hard for you to do, but this is going to be A11, C11. But now it's not going this way, it's going to be plus A21, C21 plus C31, AC31, C31. One of those indices. Along this column now. What is that going to be? Again, because it's plus minus plus in this column also, it looks like I use the same pattern, but when we use this one, oh, it's minus plus minus. Careful. So A11 is the same, 1 times C11, which is the same. I block off row 1 and column 1. 3, 5, 2, negative 1. Also, when you're doing this, you have to compute the same cofactors sometimes, so maybe keep them around. Minus A21 is a 1 times C21, which is going to be column 1 and row 2 blocked off, which is 2, 0, 2, negative 1. Plus 0 times I don't care. Literally what it is, 0 times I don't care. Equals 1 times negative 3 minus 10 minus 1 times negative 2, which is negative 13 plus 2, which is negative 11. That was also nice because in the first 2 moves I didn't have to compute one of the terms. Now let's do it foolishly along column 2 or row 2. Doesn't matter, I said column 2, stick to your guns. What does that look now? Column 2, that will be the determinant of A21, C2. No, I told you the indices will get me, they'll get you too. A12, C12 plus, now who's that? A22, C22 plus, this one is A32, C32. Column 2, column 2, column 2, row 1, row 2. Row 3. What is that? Be careful now. I'm using this column. Negative plus negative is the cofactors. Negative times A12 is negative. A12 is 2. And then I'm going to block off row 1 and column 2. That gives me 1, 5, 0, 1. Negative 1. Plus now. A22 is 3 times C22, which is the Greek cross again. We're going to block off row 2 and column 2, which is going to be 1, 0, 0, negative 1, minus A32, which is a 2 times C23, which is going to be row 3 and column 2 blocked off, which is going to be 1, 0, 1, 5. You can see even for me, that's the non-standard ones. I've trained my brain to do row 1 and column 1. I'm really fast at those ones. Other ones I'm not, but I'm just showing you that that was a foolish idea and I had to compute all the cofactors too. Either way, this gives me what? Negative 2 times negative 1 plus 3 times negative 1 minus 2 times 5, which is 2 minus 3 minus 10, which is negative 11. Either way you do it, you can use any row or any column to cofactor expand about. It'll give you the same number if you do it correctly. But using zeros or rows or columns that have zeros are much more beneficial. How can we do that? We're going to get 3 properties, and the safest property says you can manipulate one row or column of a determinant and replace it with a multiple of another one, just like in row operations. But that won't change the determinant at all. So then we're going to get a leading 1 or a leading entry and get 0 below, and then cofactor expand along that front column. Let's state the 3 properties and then we'll try that out. This is cofactor expansion along any row or any column. All right, that was computing determinants of an n by n matrix. In this case, we used a 3 by 3 for pedagogical reasons. We want to keep them fairly small. But for any size matrix, we can now compute the determinant using cofactor expansion along any row or any column. In the next video, what we're going to do is we will give you 3 determinant properties and then show you how to create a leading entry in the top corner and then get zeros below and then cofactor expand along that first column, and that will, combining the determinant properties and cofactor expansion along the first column, will give us a Matrices doll method of computing. If I have a 5 by 5 matrix, I'm going to get a 1 and then I'm going to get 4 zeros here, and then I'm going to cofactor expand and it's going to block off, and I have to compute 1 4 by 4. Matryoshka, and then I'm going to get a leading 1, and then I'm going to get 3 zeros below, and then I'm going to cofactor expand along this row, and then I'm going to get 1 3 by 3, and then I'm going to get a leading 1 and zeros. You see where I'm going with this, and I'm going to cofactor, and then 2 by 2 is AD minus BC is how we compute. This is a Matryoshka doll, and we compute any size determinants using 2 by 2 determinants, using a combination of the determinant properties we're going to show next time and cofactor expansion along column 1. This is how we compute determinants. Please subscribe below, hit the bell. You'll get notifications for the next video and many more. This is the Tutor Wizard. See you next time. Listen, kid, shit in one hand and wish in the other one. See which one fills up first.